In this video, we're going to talk about the action of a group on itself by left multiplication. So let's say G is a group. Then I'm going to define an action of G on itself as follows. So we're going to define an action G acting on G as follows. For each G belonging to the group, so I'm going to think of that as the element that is acting, and each X in G, and X is going to be the thing that gets acted on. Let's do a little color coding here. Let's have purple for that. Okay, so G is acting, X is getting acted on. And here's what we're going to do. Define G acting on X to equal just GX. Okay, nothing too creative there. In fact, it looks like I just vanished the period there. But this is called the action by left multiplication. More precisely, it's called the action of G on itself by left multiplication. All right, so what we're doing here is perfectly sensible, because what I'm doing is I'm acting on any element of the group, calling that X, and then what comes out is an element of the group as well. Okay, it's an element of the set being acted on. So X just goes to GX. I might just go ahead and symbolize it that way, that I have X going to GX. Okay, let's just quickly verify that this is a group action. So to verify this, I need to do a couple of things. I need to show that for every X in G, that is every X in the set being acted on, the identity acts on X by sending it to itself. Okay, this is true because if X is in our set, then 1 acts on X by sending it to 1X, which is just X. That's by the rules of the group G. Okay, so that's true. And then second of all, we need to show that for every X belonging to G, and for every G and H belonging to the group G that is acting, that GH acts on X the same way that G would act on H acting on X. Okay, so in other words, acting by GH is the same as acting by H, then acting on the result by G. It's always hard to get that in the right syntax. Okay, so to show this, let's just calculate GH.X. That's equal to GH times X in the group, and then by associativity, that's the same as G times HX, and then that's the same as G dot H dot X by definition of our group action. Okay, so we can check off both of these properties and say this is indeed a group action. Whee! Okay, so that's great, but what does that do for us? Well, really, the action of G on itself isn't something that we haven't seen before. We've talked about how under left multiplication, each group element, that is each G, induces some permutation of the X's, that is some permutation of the group elements. Okay, so what we're seeing here is not anything that new, but what is kind of new is thinking about what this would look like if instead of acting on elements by left multiplication, we acted on cosets. So for this, I want to just digress a little bit and do an example. So for this example, I'm going to have Z acting on Z. And this group is additive. So rather than thinking about the action being by left multiplication, I'm going to think of it as being by addition. So action by left addition, if you want. Of course, this is abelian, so left or right doesn't really matter. All right, so for example, 3 is going to act on -6 by sending -6 to 3 plus -6, which is equal to -3. Okay, and then we could even imagine what a group element does to the entire set, and I'm going to represent that using array notation. Of course, I won't be able to express everything completely, but I can at least show a few elements. So these particular elements would go to -1, 0, 1, 2, 3, 4, and 5, because I'm just adding 2 to each one. Okay, so that's an illustration of the action of a particular group element on the set Z. And again, as always, this poses the complication that we have to think of this in two different ways. We have to think of the group Z, which I'm underlining in red, but also the set Z being acted on, which is underlined in purple. All right, so anyway, what about cosets? So for this, I'm going to need to define a particular subgroup. So let's go with, let's let H equal the subgroup, I don't know, how about 4Z? So this is the subset or subgroup that consists of all multiples of 4. -8, -4, 0, 4, 8, 12, so on. Okay, what are the cosets of H? Well, the cosets of H are going to be these. They're going to be 0 plus 4Z, which is the subgroup itself, because I can think of adding 0 to any element of 4Z, and, well, I just get the same elements I had in my subgroup. All right, so that particular coset is a subgroup. The other cosets will not be subgroups. They'll just be other sets. This will be the set gotten by adding 1 to any element of 4Z. So I can just imagine taking these elements here, -8, -4, etc., and adding 1 to each of them. So that gives me -7, -3, 1, 5, 9, 13, and so on. Okay, I could also take 2 plus 4Z, and that would be constructed by adding 2 to each of the elements of 4Z. So I get -6, -2, 2, 6, 10, 14, etc. And let's see, what else? I could do 3 plus 4Z. That would give me -5, -1, 3, 7, 11, 15, and so on. But then if I do 4 plus 4Z, well, that's going to be constructed by taking all of my subgroup elements and adding 4. That gives me -4, 0, 4, 8, 12, 16. And really, that's just the same set that I have here. I just get multiples of 4 again. So that's not a new coset at all. That's the same thing as 0 plus 4Z. So I'm not going to write it down again. I think these are the only different cosets I get. There are 4 different cosets. One way that we express this is we say that even though G and H themselves are infinite groups, we can still talk about G colon H, the number of subgroups of H and G, and we can say that that's 4. By the way, this is often called, this whole notation here, this is called the index of H in G. It's the number of left cosets or the number of right cosets. Those will be the same. I'll just say number of left cosets of H in G. But now back to the whole matter of the group action. So the question is, can Z act on left cosets of 4Z in Z? Okay, so now, and this is a poor strategic choice of colors on my part, because this is now my group, and I'm going to underline in purple, even though all of this is purple. This is the set I'm acting on now. Not the group Z, not the set Z, but the set of left cosets. All right, well, let's suppose that we try acting on left cosets in this way. So I'm just going to say this verbally at first, and see if we can work this into something that qualifies as a group action. So let's say that an integer in Z, so if G belongs to Z, have G act on a coset by adding G to each element of the coset. So for example, if I wanted to have 7 act on, let's say, 2 plus 4Z, then I'm going to take every element of 2 plus 4Z, so every element of this coset, and add 7 to it. So what do I get if I add 7 to each of these? I get 1, 5, 9, 13, 17, 21, and so on. But wait a minute, if I have, let's say it again, 1, 5, 9, those look like elements of 1 plus 4Z. So it looks like if I did that, I would get exactly the set 1 plus 4Z. I haven't proven that yet, but I think that's exactly what I'd get. So I can think of adding to any particular coset, a given integer, and winding up with some other, or possibly the same coset. Like if I took this coset here, 1 plus 4z, and added, say, 16 to it, well, what would I get? I would get, let's see, 9, 13, and already I'm seeing I'm getting the same elements that are over here, the same elements of this existing coset. So 16 is going to send 1 plus 4z to itself, which incidentally would make 16 part of the stabilizer of 1 plus 4z, which is kind of nice to know. All right, so anyway, let's generalize this idea, because it looks like we can actually take elements of our group, in this case z, and act not only on elements of the group, but also on cosets of a particular subgroup. So we're going to generalize that now and prove something about it. Okay, so in general, let's suppose G is a group. And let's say H is a subgroup of G. All right, we define the left multiplication action of G on left cosets of H as follows. So for each G belonging to G, and again that's the one going to be acting, and each left coset AH, that's the thing getting acted on. Here's how I'm going to have G act on AH. I'm just going to take every element of this set, every element of this coset, and multiply on the left by G. That's it. And that's going to give me a new set of elements. I claim that that will be a left coset. It's not immediately obvious that it is. I'm going to need to show that, but that's how the action is going to work. I'm going to take G, multiply it by every element of this set, and thus construct a new set. So let's write this down. So G acting on AH is going to give me this thing called G AH. And I'm defining that to be the set of all Gx such that X is an element of AH. Notationally, I know that that looks like a left coset, but it's not quite clear that it is. I do claim that it is the same thing as the coset GAH. And we're going to show that now. By the way, why do I need to do any of this? Why do I need to show that these two sets are the same? Let's just make sure that's clear. I am claiming that G as a group acts on left cosets of H. So if I have G act on AH and it sends AH to something that is not a left coset, then I'm in trouble because I'm claiming that the group acts on left cosets. So that means the left cosets have to go to left cosets for any of this to be a valid group action. That's why I need to prove this claim. So to show that this is true, to show that GAH is the same as GA times H, I'm going to do just the classic set equality proof. So to show this is a subset of GAH, let's assume that Y belongs to G times AH. Okay, then by our set definition, this means Y is equal to G times X for some X in AH. And since X is in that left coset, that means X is equal to A times little h for some H belonging to the subgroup. Okay, so now looking at all of that, that means Y is equal to G AH. Gah, that was not intended. By associativity, that's the same thing as GA times H. And because that is the element GA times a subgroup element, that belongs to the coset GAH. All right, so I've shown that anything that's in G times AH also belongs to the left coset GAH. All right, so let's summarize. So that means GAH is a subset of GAH. All right, now the converse. Suppose that Y belongs to GA times H. So to show GAH is a subset of GAH, assume Y belongs to GAH. It's really going to be the same reasoning, pretty much in reverse, I think. Then Y is equal to GA times some subgroup element H, that is for some H in my subgroup. So by associativity, Y is going to equal G times AH. So that element there, that belongs to the coset AH. So Y belongs to GAH. All right, so the coset GAH is a subset of this weird thing I've constructed. All right, so all of this shows, therefore, sorry, my pen keeps skipping. It doesn't seem to like it when I make a video longer than 15 minutes. I think it's trying to train me to make shorter videos. This tells me that GAH is the same as GAH, which means that this coset, this thing I constructed by having G act on the left or multiply on the left by everything here, it really is a coset. It's just this coset here, GA times H. So anyway, this shows that G at least sends cosets to cosets. Now, one thing that there is still to show, and I'm going to leave this as an exercise because this video is too long already. So we know that G sends left cosets to left cosets. That's what this proof has shown. Now, prove it is an action, which means you have to have those two special properties. In other words, we need to show that 1.AH is the same thing as AH. That is, the identity sends each coset to itself. And also that, and I'm going to use letters other than G and H. I'm going to say G and G prime, I think. That G prime acting on AH is the same as G acting on the result of G prime acting on AH. So if you can show those two properties, then we have another new action of a group on its left cosets.